Welcome to a lesson with Dr. Powell. Let's talk about how we can think about integration, not just along a coordinate axis like the x-axis, but perhaps along a curvy line like this, taking the place of the x-axis. On the x-axis, we take a little piece of it called a dx, and we multiply it to a weight, usually the height underneath a curve, and maybe when we're doing an area calculation. So we have f of x times a little dx, and then in a limit, as these dx's get smaller and we're adding up the pieces between two x values, we get an integral. Well, here we want to think of it the same way, but how do we account for this curviness? This curviness comes from how it's pictured in the xy plane relative to x and y. So if we take a little piece of this curve, just like we took a little piece over here, it actually can be thought of as having two components, a dx and a dy, where this little piece we'll just label as dr, thinking of these things as vectors. Now, just like we have a weight associated with this dx here, we need a weight associated with this dx as well. But the position on the curve itself could be thought of in terms of a parameter t, but that parameter t gives an x value and a y value along the curve if you think about a set of parametric equations. So we know what the position is on the curve right here by this function of t, where the output is an x and y. Now, often when we think about something to weight to the dx and something to weight to the dy, so we're kind of going to be thinking about an integral along the x-axis and an integral along the y-axis. That's really what we're going to have, and we're just going to add those two integrals together. And that's how we're going to think about integrating along a curve. We just have an integral along the x and an integral along the y. The dx needs a weight associated with it. Now, this weight is oftentimes just a function of x and y. Of course, we precompose, or we put before these x and y the function that goes from t to the curve itself, so that this really is a composition here as we move along the curve. Let's call this curve c. So we're at a c here, meaning that the x and y values that we're going to pick come from the set of parametric equations that define the curve c. So we're going to do the same thing for y, and we have another weight associated with it. I'll just call it gxy. So I use f and g in this way, and they're just weights associated with this. Notice that they depend on x and y, and that's because we have x and y depending on t and being on the curve c. But this kind of speaks something more. This same weighting procedure can actually be used on any curve, because this function depends on x and y, and this one also depends on x and y. In that manner, let's kind of think about what we have here. It looks almost as if we have a vector, fxy, comma, gxy, dotted with dx, dy. Notice what happens, and with an integral here, what happens is this was multiplied to here, this is multiplied to here, and then we can just split up the integral into two integrals. Or we could just keep it the same integral if we just undistribute the integrals across the addition, and we get something that looks like this. So we could either write it this way, or we could write it this way. We could think of this as a vector. In fact, we could even think of it as a vector as follows: f of xy. So it's a vector function with two inputs, dotted with this vector. Now, this vector is the same as dr. Notice we have it right here, dr. So another way of writing this integral, which is along the curve, called a line integral along the curve c, is simply to write f dot dr, where we're literally taking a dot product. But all we're really doing is taking two integrals, one along the dx and one along the x and one along the y, and adding them together. But there's various ways of thinking and writing it down. This f right here is a vector function where every single point in the xy plane has an output vector. Now, if we shift that output vector from its standard position of the origin to emanating or starting at the point that's describing it, the xy, we get a vector. Vector fields, magnetic fields, gravitational fields are often described by such a vector function f of xy. So really, the question is, what do we integrate along a curve? We integrate a vector field. Vector fields can be integrated on curves. Functions right here are integrated along coordinate axes. Of course, you could actually interpret this situation here as a very simple case of the vector field idea, where you have a lot of zeros and components, but it still works. So the generalization is, again, we integrate a vector field along a curve via a dot product. We can write it in this form, or we can write it in this form. This form right here is called a differential one form. Notice you have something times dx plus something times dy. It can be thought of as integrating along a line of x and along a line of y and adding the results together. Now, how is dx related to the actual curve where we're going in dy? Well, simply as follows. Dx is equal to x prime of t dt. So if we can write this as a function of t and dx in terms of dt, we just have a single variable integral to solve in terms of t. Similarly for dy, if we were to do this integral, using the idea that dy is equal to y prime of t dt. So this is a little short description and motivation for what we're about to do with what are called line integrals, or integrals along a curve. Thanks for watching.